Okay, so we have that image going over a cylinder, and then you can imagine, and you can actually form this idea of this, right, the pressure that's happening, and here's your gauge reference pressure. This could be atmospheric, so, right, we could just make this sort of the pressure, the thing we're looking for. Just like how before, remember that we had remember how that was the thing we looked at for the boundary layer. Now we're going to talk about that pressure. We look at these coefficients of drag, form drag. And here there are the three cases. If it was a totally inviscid theory, you can actually write out what this would happen as I go along the surface. So this is right going from A. This is going to go from E, so it goes all the way to E. You have to keep that picture in your head, but this is sort of my streamline coordinate, and here's this coefficient of drag right now. So, and then here is separation. So this is going to be point C. So for the inviscid, this one, it's the bottom one. That's where mathematically you have to have absolutely zero viscosity. If that's the case, you have the Euler equations of motion, and this what happens, you have total pressure recovery. That's not what happens because there's always losses. So for any non-zero viscosity value, this graph is slightly altered. So you start here, and then turbulent one, and the turbulent one, you'll be behind, you're right, this C will happen before the inviscid theory, but after laminar, that's important. So you go through, this doesn't go as deep as much, and then what happens is you get not as much recovery as the inviscid. There are still losses that happen because of the friction of the fluid. And actually laminar, there's a situation where now you've released furthest back and you recover the least. So the important points is that this never happens. This is inviscid. There is a surface, so this can't happen. But this idea that you come out is that turbulence delays separation when compared to the laminar. The laminar will separate earlier than the turbulent boundary layer. And the other thing is this was something called a paradox of this situation where you couldn't recover, and it's the idea that there's always separation. There will always be boundary layer separation if you have a non-zero viscosity. And there was some paradox back in the day that was satisfied because of that. And think of it as like, whenever we did those boundary layers, every Reynolds number had an X value in it, right? That we were calculating, right? So we had this velocity, and there was a variable X, right? And then we knew that it always tripped into turbulent to begin with, so that all boundary layers are just going to keep growing and growing even on a flat plate scenario. They're just going to separate earlier if it's on this curved surface. So I think there's some line you can even draw right here to get a better picture. But this is the main image that you care about, though, is these coefficients of drag. And this is this is just a classic image for a cylinder sitting in flow. It's the one I've drawn here. Right? This body in this field, as I go along some surface like this, has this coefficient of drag behavior. But other surfaces will have very different shapes of this. But you'll notice that they're all kind of the same, and really, the idea is get graphs for these coefficients of drags so you can calculate this, so you can plug it into to calculate forces. So you hope you appreciate these non-dimensional coefficients of drags are so helpful, because if I have the graph of it, that means if I know these values, I can look at my graph and I can get the pressure. So they're very important, and we make them all the time. Okay, so the idea is that curved surfaces even other thing to make this true, the idea is that the curved surface means that this is now not a constant value. right? So if you remember, we had this expression here before. Remember, this is the momentum thickness from the boundary layer. So this is important because before, when it was constant value, you got this. So right from that idea, you should understand the free stream velocity can tell you something about the shear at the wall if you know the boundary layer. So you can redo the whole process, but the thing is, I think I told you before, there's this extra term that happens if this is a non-constant value, and it's called the von Karman integral relationship. So now, this idea that free stream velocity tells you something about shear still happens, and it's written a couple ways. Okay, sorry. I should have put a square there before I did. I should have put a... Yeah, I messed up writing it last time. There should be a ds there. So, right, for a curved surface, you get this extra term. Right, if it's a constant, that term's out. You recover the flat plate shear. Any curvature, this now plays a role, and now it's telling you something about shear. So this is a very well studied and very incredibly difficult equation to have, but sometimes you can estimate shears just based on it alone. You would just need to have some idea of what this is, where you are there, some estimate of what the boundary layer, of what the displacement thickness is and the momentum thickness. You get an idea. That wasn't given in my class, but I do like this because it really ties together how this free stream velocity is telling you something about the shear at the wall. And it's just a natural extension of what we did before to figure out shear at the wall based on free stream velocity. Even though a changing free stream velocity, we looked at it to get pressure differences, but you can see it actually gives added shear stresses based on this equation. I have an extra credit I believe I have is like, well then when does separation? That was extra credit. That was derived then. It's pretty simple, but when is separation based on this equation? What is the condition for boundary layer separation? Okay, so again, we're just chugging along and doing a bunch of plots and stuff, but the idea is still just this. That's the whole goal, right? And remember that we were just trying to find graphs for these things. And if you have these graphs and you have Reynolds numbers, then you can get at what these forces are. So for the skin friction, we looked at the analysis of boundary layer to get an estimate, right? So this was about estimating the shear stress at the wall, and this was a streamline analysis to get, well, how does the pressure vary? But for the most part, you're always just going to get a bunch of experiments you end up doing and well tabulated. Or you don't do the experiments, you can just get really rigorous in that shear stress or all those equations, and you can just plot them in a numerical thing to maybe make your own numerical plot. That's actually pretty hard, I think. Okay, so then you have these two perpendicular ones. You actually have a lift. And then down here you'll have drag, right? So, right, you really are just looking for these graphs right here, so you can do exactly what you did with friction factors, right? And you can calculate what this is. If you move this to the other side, you now know what the skin friction is. If you can calculate what this drag coefficient is or have a graph for it, you can move this to the other side and get what the form drag is. You can get power values for doing that. So, right, the idea is you're looking for these to figure out, right, this idea of what's the force to get the velocity. This is actually, the lift force is the separate one. That's for flights and airfoils. And you actually would know what the lift force is because, well, right, it has to oppose the weight. So that's not too bad. So, the idea of this external flow, at least in the pressure form, was just to take care of this one. More analysis was done in the skin friction because you could come up with these, right, come up with some math of relationships where you could get these, like, right, these functions of Reynolds numbers, right? And then we made the plot even of what you could do the Moody plot based on other equations you get from boundary analysis to get what this skin friction was, right? And again, it had the Reynolds number. It's just a CF instead of little f, like a Darcy friction factor, but you had the same sort of transitional thing where something like that, where this is now rough and this could even be included. And that's the skin friction. This we don't have in internal flows, though. I mean, you could have some analogy to it, but this is the idea where I think before I had mentioned how I think Moody charts or using a Moody chart can be kind of outdated just because of how, all those equations to make the Moody chart for your internal flows, you can look them up and you can program them. But it's different for externals because it's so complicated. You're always looking for this, right? This is the really, really big one that you want. And sort of this is sort of for optimizing. Right? Or like long bodies that have a lot of drag or a lot of surface. This can be important, but this is really what you want to get at for those external flows. And this graph, like that weird dip one I showed earlier, they're really strange. So for external, I think graphs are, right, rule the land because, a lot of times they are coming from experiments or, crazy numerical things that could be garbage. But I'm going to go over how to look at the graphs next.